Welcome back to the Deep Dives. Today, we're doing something a little different. We're not looking at the latest AI breakthrough.
No, not at all.
Instead, we're actually looking backward to look forward. We're diving into this really profound philosophical critique of artificial intelligence that was first written, believe it or not, back in the mid-1960s.
That's right. And this isn't about, processing speed or how much data you have. The source material we're looking at, it really hits the foundational assumptions of the entire field.
Yeah.
It argues that the limits we saw decades ago are, well, inherent to what a digital computer actually is.
Okay, so we're talking about the stagnation that happened really early on in AI's infancy, what they called cognitive simulation.
Exactly. The programs from about 1957 to 1967.
And the big question this critique raises is, why did all that early success in really simple tasks just completely fail to scale up to genuine adult-level intelligence?
And the author argued back then, and still a really potent observation, that these setbacks weren't just temporary engineering problems.
Not just a matter of waiting for better hardware.
No, they were signs of these deep philosophical dead ends, impasses that are just inherent in trying to model human reason with a machine that can only operate on explicit, unambiguous rules.
And the stakes are just as high today. I love this quote from the material, that these issues are too scientific to be left to philosophers and too philosophical to be left to scientists.
It's a perfect summary.
So our mission today is to unpack what those early failures can teach us about what makes human intelligence so unique, and maybe what makes it non-computational. Okay, so let's start with the optimism. Where did it all begin? Why did everyone think the digital computer was basically the finish line for recreating reason?
Well, it's because for centuries, the whole Western intellectual tradition has basically defined reason as being the same thing as calculation.
It was an old idea.
A very old idea. It goes all the way back to Plato, who demanded that for something to be knowledge, you had to be able to write it down in explicit definitions or rules, what we'd now call an effective procedure.
So if I can't write it down as a clear step-by-step process, it's not really reliable knowledge.
Yeah. Exactly. And this idea got super explicit with thinkers like Thomas Hobbes in the 17th century.
Right.
He literally wrote that reason is nothing but reckoning. Just adding and subtracting. It is all syntactic. You're just moving symbols around based on rules, not based on some messy internal meaning.
And then Leibniz comes along and sort of builds the tools for this.
Leibniz is key. He co-invented calculus. He developed the binary system. He formalized the ultimate goal. He wanted to create a universal characteristic so that any problem, moral, scientific, whatever, could be solved by just saying, let us calculate, sir.
Let us calculate, sir. I mean, that just perfectly captures the whole ambition.
It really does. So the digital computer, which operates on these unambiguous bits of data with strict formal rules, it was seen as the physical manifestation of this centuries-old philosophical dream. A machine that calculates without needing any intuition or judgment.
And as soon as machines were there, people like Alan Turing set the targets, the Turing test, back in 1950.
Yep, a behavioral test. And that immediately pointed all the research at things that seemed rule-based. So chess, language translation, things like that.
Which brings us right to this paradox you mentioned earlier, the fallacy of the successful first step.
Right.
You defined it as this pattern of an early dramatic success and then diminishing returns, disenchantment, and pessimism. So what did that look like in reality?
It looked like chess. In 1957, the first programs could beat a beginner. And this led pioneers like Herbert Simon to predict very confidently that a machine would be world chess champion in, a few years.
They thought it was a straight line, just add more computing power.
They did. But that path wasn't linear at all. That initial jump just stalled.
Famously.
The big Newell, Shaw, and Simon program was beaten by a 10-year-old novice in 1960. The problem wasn't calculating a few moves ahead. It was the exponential explosion of possibilities. It couldn't handle it.
And that's the zeroing in problem, right? A human grandmaster isn't calculating millions of moves. They look at the board and they instantly zero in on maybe 100 or 200 relevant possibilities.
Yes, based on a global organization of the board, they see patterns, threats, structure.
Whereas the computer has to rely on counting out brute force.
Pure brute force, yeah, guided by some very simple heuristics. But as the game gets more complex, that counting out just hits a combinatorial wall. No amount of speed can fix it. It just shows this fundamental structural difference in how we solve problems versus how a machine has to.
Okay, hold on. Let's map this to today. You look at something like AlphaZero, which learns by playing itself millions of times. Hasn't it basically solved that zeroing in problem? It seems to have a sense of global organization.
That's a great critique, but the critique still holds, I think. AlphaZero didn't get there by suddenly acquiring human-like insight. It got there by making the counting out process ridiculously efficient.
This is still brute force, just smarter brute force.
Fantastically smarter. Guided by these incredibly refined, machine-learned heuristics. But its success still depends on making way, way more calculations than a human does. And that insight it has is totally opaque. It's brittle. It breaks down if you give it a problem that's even slightly outside its training.
That brittleness is key. Let's talk about language, because the same thing happened there.
Oh, yeah. The early machine translation programs hit the exact same wall.
The first step seemed easy, a mechanical dictionary.
Word in, word out. Simple. But language is just drowning in context and ambiguity. The classic example from Bar Hill is perfect. The box was in the pen.
Right. A human instantly knows that pen means a playpen, not a writing pen.
Of course. Because a toy box doesn't fit in a BIC pen. Yeah. But for a machine to know that, it needs more than a dictionary. It needs access to this potentially infinite database of facts about the world.
The relative sizes of objects, the purpose of a playpen.
All of it. It needs knowledge of the world just to figure out one simple, ambiguous sentence. It's an impossible task.
And this feeds right into the challenges they had with the general problem solver, or GPS.
GPS was great at toy problems, like the cannibal and missionary puzzle, where every rule is perfectly laid out.
Oh, the variables are known.
But real-world problems require insight. They require you to grasp the essential structure. It's almost a Gestalt idea from Wertheimer, seeing the deeper structure of the problem.
And the critique of GPS was that the machine wasn't actually having that insight.
Not at all. The programmers were. They had to sort of surreptitiously feed the machine the crucial distinction between what's essential and what isn't. They built the heuristics of planning before the program even started its search.
So the computer was just executing a plan that a human had already structured with their own insight?
Precisely. The hard part, the structuring, was done by the person. The machine was just following the insightful rules.
Okay, this is a huge realization. So if we look at the pattern across chess and language and problem solving, this critique identifies 4 specific human abilities that just kept defying the programmers.
Yeah, 4 things that seem impossible to pin down with explicit formal rules. Because it depends on us being in the world, not just processing facts about it.
Right, lay them out for us. What's the first one?
The first is fringe consciousness. It's basically our ability to ignore irrelevancies. When you walk into a room to find your keys, you automatically zero in on the task. You filter out the color of the walls, the hum of the air conditioner, the dust in the air.
Right. But a computer has to process or explicitly exclude every single one of those facts unless it's told not to. It has no fringe.
None. It's like asking a search engine a question about horse racing, and it has to first confirm that all the articles about centaurs are irrelevant before it gives you the answer.
That's a great analogy. Okay, what's number 2?
Ambiguity tolerance. We just talked about this with language. We navigate ambiguity constantly, and we do it smoothly because the context just narrows the possibilities for us. We don't need to turn every situation into a precise logical statement before we act.
Like when you hear a change in someone's tone of voice, you know it's sarcasm. There's no rule book for that.
Exactly. The third is essential discrimination, or just insight. It's what we saw with problem solving. It's the ability to look at a complex, messy problem and just grasp its deeper structure, figure out which parts actually matter.
Which is often context dependent, right? Not something inherent in the rules of the task.
Totally. And the fourth capacity is the recognition of typicality and family resemblances. This one is fundamental. It's how we recognize patterns even when there are no strict common features you can list.
Okay, I need an example for that one. If I recognize a chair, surely I can list the rules for what makes a chair a chair.
Can you, though? I mean, the philosopher Wittgenstein pointed this out with the category game. Think about it. Chess, solitaire, baseball, hide and seek. What's the one single trait they all share?
Huh. There isn't one.
There isn't one. We know they're games because they have these overlapping similarities to a paradigm case. Our brain does it by analogy and proximity, not by running through a checklist of necessary conditions. A machine needs that checklist.
Wow. Okay, so our brain is built for analogy. The machine is built for the checklist. That's a huge difference. And this is where it gets really deep, because the critique doesn't just stop at listing these missing skills. It attacks 2 fundamental philosophical assumptions that AI inherited from the entire Western tradition.
Right. The first one is called the ontological assumption, which is really just the belief that the world can be broken down into a set of context-free, discrete, independent facts, like entries in an encyclopedia.
The database fallacy, the idea that if you just gather enough facts, a trillion facts, intelligence will just emerge from it.
Exactly. Minsky said something like, "A million facts should be enough for a very great intelligence." But the critique says, our knowledge is nothing like an encyclopedia. We know what a chair is, not because of a list of facts about its shape. We know it because of its relationship to our own bodies, to fatigue, to the need to sit.
So relevance is baked in from the start because we are in a situation. We don't gather facts and then figure out if they're relevant. The situation itself tells us what's relevant.
Correct. Without that sense of the situation, a machine has no way to organize facts. It's just noise. It might as well pull up facts about centaurs when you ask about horse racing.
And that leads directly to the second major point, which is the role of the body. The early AI folks really pushed this brain in a bottle idea. The body is just messy hardware.
Just an input-output device. But the counter-argument is that the body is absolutely essential for intelligence. It gives us all these non-computable skills that come before formal logic.
So give us that famous analogy, the skilled tool use.
Think of a blind person using a cane. After a while, they aren't calculating the angle and pressure of the cane on the ground.
No, they're just feeling the ground.
They're feeling the ground through the cane. The tool becomes a transparent extension of their body. They're operating on a phenomenal level, not a physical, calculative one.
It's a seamless integration.
That smooth, skilled performance, that muscular gestalt, it's not a sequence of discrete, rule-governed operations. And that's the only thing a digital machine can do. Our body organizes our world for us before reason even gets started.
That's an incredibly powerful idea. You could perfectly model the logic of the brain, but if you miss the embodied situational foundation it's all built on, you've missed everything.
So if you put all this together, the zeroing in problem, the need for context, the four missing capacities, the central finding is that intelligent behaviors are fundamentally discontinuous.
Discontinuous? What do you mean by that exactly?
It means there's a huge qualitative gap, a chasm, between simple rule-based things like a checkers program and complex human things like understanding a joke. The hard stuff is structurally different. You can't cross that chasm just by adding more speed or more data.
Which is why that first successful step never led to the next one.
It couldn't.
So, bringing this to today, what does this mean for applied AI? If this critique holds up, then the ultimate goal of a fully autonomous, adult-level machine intelligence, it's just philosophically doomed from the start.
Well, the source material points to another path, the one it saw as the only truly promising one. Human-machine cooperation, augmentation.
The partnership model.
Exactly. Computers are amazing at counting out, at formal, discrete tasks. Humans excel at zeroing in, at flexible, open-ended understanding. So the most powerful approach is to couple their strengths.
That sounds so much more realistic than the replacement model we hear about all the time.
And it has a track record. Even back then. Look at the SAM programs, how automated mathematics. On its own, the computer's logic was just too slow, it got lost.
But with a human.
But when a human mathematician provided the high-level guidance, picking the starting formulas, pruning the search space, deleting unimportant steps, the machine, now armed with human insight, was able to solve a real open problem in lattice theory.
That's a perfect example. The human provides the structure, the context, the insight, and the machine does the heavy lifting, the massive calculation within that framework. It's a real-time interplay between man and machine.
It really augments our intelligence instead of trying to replace it. It reminds us that the machine's greatest value might be in what it lets us do by taking care of the parts we find tedious or impossible to compute.
This whole deep dive has been. Well, it's a powerful reminder that the limits of these machines really force us to look at what makes our own reason so unique. Our embodied, situated, context-aware way of being in the world.
It really does. The author of this critique, Hubert Dreyfus, he argued that this moment in history was a choice. We could either face the truth of the tradition's deepest intuition, that reason is calculation, or to abandon what has passed for an understanding of man's nature for 2,000 years.
Wow.
So, thinking about the relentless push today for these huge autonomous AI systems that still, fundamentally struggle with common sense and context, which side of that historic divide do you think we're standing on right now? And what does that answer mean for how we understand ourselves?